All right, hello everyone. Welcome back to Physical Geology 1403, Lecture 5. You're in week 3. Congratulations. You've made it past the quarter of the way mark. It flies, doesn't it? Oh, time flies when you're having fun. Who's having fun? Good. Who thinks this class is interesting so far? Hopefully more hands. Okay, good. Thank you. I appreciate that. Volcanoes. We talked about volcanoes last time, right? Interesting, fascinating, fun, terrifying, right? Hopefully that was your takeaway. A healthy respect, but also deep interest in volcanoes. That's my aim. Okay, so today we are lecture 5. We have 3 lectures left in module 1. So 5 today, 6 next time, 7 next time we meet next week on Tuesday. And then 2 weeks or 9 days, I should say, from now. 9 days from now is when we will have the first exam review. And that will be here in class. Those of you that are coming to be here in class, please come prepared with questions. I do not have a formal, here's an exam review sheet. I go based entirely off of your questions because those are your specific needs. When you're going through your notes or you're reviewing the lectures or anything like that, that's the best metric for where we need to focus on, where your notes are weak, I guess I should say, is where we need to focus on for our exam reviews. And so that's how my exam reviews are driven. For those of you that are watching this class online, hopefully you get this notice far enough in advance. I mean, it's 9 days from now. Hopefully you're watching this more than 9 days before the, or at least 9 days, but no more than a day before you need to prepare for the exam. Email me your questions and I will address those in the exam review here in the recording that you can watch before you take the exam. Make sure you get those questions to me no later than Wednesday night. So that's the night before our final exam review, or not our final, well, our exam 1 review will be. All of you can just bring them here and we'll talk about them. And then we'll have normal lab time after the review, but immediately following the review, I will open the exam. Okay, so you can choose to stay here and take it, or you can focus on lab and take it at home, the exam at home, whatever you want. All right. You have 2 labs assigned. You are not getting another one today. You will get another one in 2 days, the next time we meet on Thursday. Okay. So you should be working on labs 1 and 2 at this point. A fair number of you have already turned them in. I will say a surprising number of people turned in blank sample identification sections. Blank is still wrong. You have nothing to lose by at least, putting an educated guess in there. Like if it's hard and you can't figure out more than a few properties, use those at least a few properties to try and figure out what you're looking at by comparing it to the spreadsheet, right? Just to reiterate, your process by doing these labs is you're observing the properties that we learn about in class, like with minerals, optical property, cleavage, crystal form, all of those. You are observing those either here in the classroom or by watching my videos that I provide on my YouTube channel for my online students. And then you are recording those properties you observe on that assignment, and then you're comparing those properties to the Excel spreadsheet, which is in the lab resources folder. That Excel spreadsheet's your best friend. It has all the possibilities of what you could be looking at on there. You have nothing to lose by putting one of those names on there. And so leaving it blank is going to end up with a wrong answer. And so when you go back and I've graded all lab 1s that were turned in up until yesterday. Okay. So if you go in there and you see your grading, like, why did I get a 32 out of 60? That might be why. Or you could have just got it flat wrong. In either case, feel free to try again. Labs you can take as many times as you want. Labs are a learning experience, not a summative experience. They're a formative experience, okay? That's how I have them structured in my class. You can take labs as many times as you want. You can ask me for help on labs as many times as you want. You could have everything in the class done. And then 2 days before the end of class, you feel like you're really prepared for the final, but you know what? I got that 71% on lab 1. Feel free to work on it again. Okay? As many times as you want because it is for your benefit to learn it. One other thing I noticed was that some people were putting non-mineral names on the minerals lab. This is, I don't remember exactly if this happened exclusively with my online class, if there were some in the in-person class. There were a couple who did this though, where there were things like fossil limestone and sandstone on the mineral lab. I'm like, no. Those are rocks. Those come in later labs, right? If you look at the Excel spreadsheet, you'll see that I have it separated into lab 1, lab 2, lab 3, lab 4. And they're color-coded as well, so you can tell the difference easily between them. So please make sure that you are staying within the bounds of each individual lab when you are trying to identify what those are. There are only 51 possibilities for lab 1, not 117, right? Okay. Any questions about labs or about the class moving forward? 17, 19, 21, 23. I think that's our full class complement. Would you mind closing the door for me, Sage? Appreciate that. Okay. I think we're missing Joe. I think that's our only regular who's missing today. Okay. Shall we begin then? Yes? Today we are talking about weathering and soils. Can anyone tell me what weathering is? I feel like you want to raise your hand, Daisy. Do it. Thank you. Okay, so let's focus on the first part that you said, and I'm going to repeat what you said because for some reason my second microphone that I usually put over there did not charge between now and our last session, so it's dead. So I'm just going to repeat what she said. She said the process of rocks breaking down due to weather and other processes, right? That's great. Yes, weathering is the breakdown of material. It doesn't just have to be rocks. Maybe you've read some classic literature and they use the term weathered to describe something. Like, sure, like a weathered rock face or a weathered tree trunk, or they describe someone's face as having a weathered appearance, like weathered skin. Like maybe you read a Jane Austen novel or something where that was a description, or a Western, and they said, oh, he had a rugged, weathered appearance, something like that. This term means something that has broken down or is in the process of breaking down. Something that looks run down, something that looks kind of old and beaten and broken, okay? Weathering is the process by which things break down. And what causes those things to break down? Daisy said some of it. Weather, sure. I know that weather is in the name weathering, but that's not necessarily an exclusive factor. Sure, weather, but weather as an aspect of what? Overall, huh? Water, sure, can. Oxidization is a great example. That's great. We'll come back to that in a minute. But this is all a product of what? Time is a huge factor here. But Earth is dynamic. Earth is dynamic, which means that things are always changing. And if things are always changing, things are always breaking down and reforming. That's a major aspect of changing, of dynamic Earth, right? So Earth is always dynamic. And because of that, things are constantly getting weathered and broken down because they are always seeking to find a state of equilibrium, but there's another term that I used for that not long ago. I've used it a few times in the class. In general, everything in nature is seeking to find a state of... Oh, I heard someone start to say it. Starts with st and ends with ability. Good. Okay. Good. Stability. Isotopes will break down until they reach a stable condition. Rocks will break down until they reach a new stable condition. You'll see this pattern over and over and over in my class. Okay? You'll see a lot of it today. You've seen a lot of it before. You'll see a lot of it in the weeks to come. Now, what does a stable condition mean? This is when, yeah, it reaches an equilibrium, but with what? The surroundings, its environment, whatever that environment may be, on the microscopic scale or the macro scale, right? Things in nature seek a state of stability with its environment. If it reaches that point, it's good, it's done, it doesn't need to change. But until it reaches that point, it will change. Earth is dynamic. Okay? Some examples of this. Plants, they will grow, they'll flourish, then they'll die and they'll fall down. And then what happens to them? They rot away. Have you ever gone up to an old tree trunk that's obviously been on the ground for a long time and you kicked it and it just like fell to pieces because it was so rotten? That's weathering. Okay, oxidization, right? You said oxidization. What is that? It's rust. What is the process of something rusting? That's when you have free oxygens, usually in water, right? And those bond with the ferric compounds in iron or other metals that haven't been treated to prevent oxidization. And that makes ferrous oxide, okay? AKA rust. That red dust that's on all of your stuff that you thought was protected, right? You ever, I don't know, just bless you, this probably isn't an experience all of you have had, but buying a block of nice chef's knives, right? And then the first time you put them in the dishwasher and you pull them out and there's little rust spots, I guarantee at least some of your parents have felt that pain, right? And that's when you realize, oh, they lied to me, right? And then you have to hand wash it forever, and it's annoying every time you think about it. And you remember that one time you put it in the dishwasher. That's the block of knives I have right now. That's what I'm dealing with those. Okay, good. Now, there is another word that people often use side by side with weathering, but they confuse them with each other. And that word is erosion. Now, I want to make something clear here. Erosion and weathering are two totally different things. Weathering is the breakdown. The actual, in this case, physical, but there are other types that we will talk about. The actual breakdown of material is weathering, okay? Erosion is the process of transportation. It comes in a few flavors, right? Things fall down. Things are transported by water. Look at all the sediment in this river, right? That sediment is being transported, aka eroded. So when you hear someone use terms like the mountain is weathering away, what they actually mean is that the mountain is weathering away and the material is being eroded to somewhere else. Okay? Be specific, Bob. Right? You guys get that reference? Really? You guys don't watch The Incredibles in your generation? You ever seen The Incredibles? Please tell me you've seen The Incredibles. I said, be specific, Bob. Yes, in the office with his boss, and he's getting fired. You're fired! Yeah, right? He throws him through the wall. Yeah. Oh, it's a great movie. Great movie. So quotable. Where's my super suit? Right? Samuel Jackson. Doesn't get better than that. All right. Now, one type of erosion that has nothing to do with water or wind or any of the factors that you would typically think about is mass wasting. Mass wasting is what we call it, and I'll play this again, when stuff falls. We'll talk all about that later on, but stuff just falls, okay? Why does it fall? What causes it to fall? Gravity. Gravity-driven movement is called mass wasting. It's a special sort of side part of erosion that we will discuss in depth at a later time. Yes? To what? Bed what? Bed rotting. I have never heard of that. Is this a thing that I should know about? Like a bum. Like everyone wants to be doing right now. Oh, okay. Okay, so you're just sitting in your bed, you're doom scrolling, and your whole day is gone before you even note it. And that's bed rotting, as you call that? Oh, that's a disturbingly appropriate term. I will remember that. No, it's not like bed rotting. It's the opposite. The Rock is not just staying in bed. It's like, you know what, gravity? Sure. Woo! Right? I'm going to go for a ride. Okay? Now, there are two types of weathering you're going to learn about today. The first kind is called mechanical weathering. This is the actual physical breakdown of rock material. big rock becomes small rocks, right? It's pretty easy to understand. You can comprehend that, right? If I take a hammer and I smash it on a rock here on my desk, I'll break my desk, but I'll also break the rock, and there will be pieces everywhere, and it'll go in your eyes, and it'll be cool. But it'll be everywhere, right? Tiny pieces. So I'm going to tell you something, and then we're going to discuss why this is the case. As material, rock material, is reduced to smaller and smaller pieces, the pace at which this mechanical weathering occurs increases. Why? It's smaller and there's less of it to break down, but I'm keeping the same amount of mass, let's say. The overall rate at which all that material breaks down will increase as the pieces get smaller. Why? What about surface area? Break it down for me. Paint me a word picture. What is surface area?
The square, like the surface. It's measured by like square feet, square in meters, square centimeters.
Sure, but what is it? That's how we measure it, but what is it?
The measure of the area. It's like a perimeter, but for 3D.
It's not a piece of mass. It's not the amount of space that an object takes up. That's volume. We're getting closer. Volume is the entire mass, or it involves the entire area that the entire thing picks up. Surface area only has to do with however much of that mass is exposed to its environment. Bless you. Right? Every amount of mass, right, that is exposed to its environment is part of the surface area of an object. Every outer surface of my body counts as surface area. Same thing for every other object. Now, if I have a large rock, sure, it's got a lot of surface area because it's large. But how much more mass is inside of it? Way more than is exposed to the environment, right? So if I take that much mass and I reduce it, that's more of what used to be inside of the larger mass that is now surface area, right? So if I have a unit of rock, let's call it granite, that is 2 units, we're just going to call them units, to each side. That means that each side has 4 square units, right? But if I take that and I chop it up into 1 square unit sides, then all of a sudden I go from having 24 square units, I have 48 square units. Then if I chop each one of those in half again, I'll end up with 96 square units exposed to the environment. So the more surface area that's exposed, that's the more that the environment can weather it down. And therefore, as my mass gets chunked into smaller and smaller pieces, the rate of weathering, mechanical weathering, increases. Okay? The smaller the things get, the faster they will break down, basically. Overall, when you're thinking about the mass in general. Okay. The corners will weather first. Have you ever walked in a stream or gone to a river? I know they're kind of rare around here. But you ever go to one of those and you pull a rock out of it and is it sharp cornered? Does that have a lot of sharp corners and edges? No, it's rounded. We call them river stones, right? How does that happen? Why does that happen? Sure, it gets tumbled, it gets moved, it gets weathered. But why does it take on this rounded shape? Eroding sediment can bump into it. Yeah, sure, but why the rounded shape? Why are the corners more likely to weather first? There's more surface area at corners. If I take, just like if I were to take a bite out of this right there at this corner, I would be biting off more surface area than if I were to just take a bite out of one of the sides. I'm getting a chunk of the surface area from each one of these sides as a part of that corner. Corners having more surface area, weather faster, boom bada boom, river stones get rounder over time. This is true of tiny little grains of sediment as well. If you ever look at grains of sand, you ever go to the beach or the river again, you like pull up a grain, like a handful of sand and you look at it, most of them are nice and roundish. Same process. Rocks get broken. The more they get broken into smaller pieces, the faster that mass will weather. And as it does so, they take on a more rounded appearance over time. The rounder my grains are, in general, that means the more it's been weathered. Cool? Remember that. That'll be important later. Okay. Some examples of mechanical weathering. Frost wedging. If I have a large body of rock with cracks, rocks develop cracks and crevices and all throughout it, water inevitably is going to leak into those cracks. Every time it rains, water's going to go in those cracks, and it's going to stay there for a while. It's not really open to the environment enough to evaporate away, probably. And then as seasons change, that water eventually starts to freeze. What happens to water when it freezes? It expands. Actually, by on average, about 9% it will expand. Believe me, we'll talk about how fascinating water is later on in Module 2. But it will expand, and as it expands, what does it do to the rock? It shoves the crack wider. It pushes that crack just a little bit wider, maybe only a millimeter, maybe a couple millimeters, right? Maybe if there's a lot of ice, maybe a few centimeters. But year after year, it shoves the crack wider and wider until finally the crack is so big, chunks of rock just topple off of the side of our cliffside or whatever our body of rock is. This is called frost wedging. That's an example of mechanical weathering. Was that a sneeze? Those are the quietest sneezes I've ever heard in my life. Gesundheit. Okay, salt crystal growth. Very similar to frost wedging, actually, okay? So you have some opening in your rock, and rock is near enough a salty body of water. Can anyone name a salty body of water? No, good. There was one time when I asked that question, and there was just dead silence. I was like, a salty body of water. And someone said, the Dead Sea. And I was like, good for you for knowing that one. But there was a more obvious one. Yes, the ocean. Okay, there's plenty of rock next to the ocean. And every time that salty water washes up on this, maybe during high tide, what does it leave behind when it goes away? Salt. It leaves a little bit of water, salty water. That water evaporates away pretty quick, but you know what can't evaporate? Salt, so it stays behind. And you get the development of salt crystals in these little crevices, and as they grow, they start flecking off little pieces of rock around them, and so you end up with this kind of pockmarked rocky surface where there's constant saltwater activity on these rocks. This is called salt crystal growth. Incidentally, this is the same reason why after every winter, we have lots of potholes in our roads, because we put salt on our roads to keep the water from freezing, right? We don't want ice on our roads, so we put salt on the roads. Salty water has a lower melting or freezing temperature, right? Because it's salty. And so to prevent it from freezing, we put salt on the roads. That salt goes into the cracks of our road, crystallizes, cracks our roads, and makes our potholes. To prevent this from being an exorbitantly expensive thing every year, many of the northern states don't actually put salt on their roads anymore. Most of the states that I lived up in the north, like Montana and North Dakota, most places out there, most cities will instead put sand for traction, or in some places where they have a lot of it, they'll actually put volcanic cinders or ash for the same reason. Something that can give tires grip instead of simply salt to keep the ice from forming. It's much cheaper in the long run. Sure, there are maybe a few more accidents because people don't know how to drive on a traction-y surface instead of a road. But in the end, they don't have to spend millions of dollars every year repairing roads. We don't get enough snow and ice down here to learn, so we still have salt. Okay, some other examples of mechanical weathering. Sheeting. Let's return to this idea of things seeking a state of stability. Here's a scenario. I have an igneous pluton that is formed underground. Remember, an igneous pluton is a magma chamber, essentially, that formed underground. And it made a granite. This formed underground deep enough and slow enough and hot enough to make a granite versus, its extrusive equivalent, a rhyolite. So this granite, which formed deep underground at a high pressure and temperature, as time goes on, is maybe getting pushed to the surface, or the surface is weathering down towards it. Either way, it gets exposed at the surface. Is the environment at the surface anything like the environment that rock formed in? No. So what's it going to do? Huh? It's not like the environment that it formed in. The surface is not like the environment that rock formed in, that pluton. Therefore, what is the pluton going to do? Break apart in an effort to find stability. That rock is not stable under surface conditions. Boom, bada boom. It's going to break apart to try and find a new stable condition. So, a body of rock that was formed under high pressure, when exposed to low pressure, is going to start expanding outward. But rock can't expand very well. It's a hard material. And so what happens is, as the outer surface tries to expand outward, it expands away from the inner parts. And so you get these sort of cracking eggshells that fall off of our outer surface. We call this sheeting. Okay? This is, so our pluton is exposed, then stuff gets sheeted off the sides. This is a real life example. It looks like literally like eggshells. Like you peel off one eggshell and there's another eggshell under it. And then you peel off that and there's another eggshell under that. Right? That's why it's happening. The outer surface is expanding outward, cracking away from the inner surfaces and falling off. And then, of course, there's biological activity. Trees, right? Trees will often grow in the cracks in rock. As they do so, even though it may take decades, just like with that frost, just like with that salt, the tree's roots are going to force those cracks wider and wider until eventually rocks fall, right? This tree has shoved its roots all the way down into the crack in this rock. Eventually, this tree gets so large, its roots get so large that there's not enough rock over here holding onto that rock, and that rock just falls off the side. So biological activity can also cause mechanical weathering. Any questions about mechanical weathering? Good morning. Okay. Now that I think pretty much everyone is here, I'm just going to remind you all that today I will be ending at 11. I have an online training I'm required to be at. They couldn't schedule it when everyone was available, so I got the short end of the stick and I scheduled it when I am typically in that time, but I have to attend it. I will be available to answer any lab-related questions following that training. It should only take 30 or 40 minutes tops. Okay, so we'll keep going here for about another hour, and then I'll end for lab time at that point. Okay, so that's mechanical weathering. The other type of weathering is called chemical weathering. Chemical weathering is not the physical breakdown. It is the chemical dissolution. Have you ever poured water or salt into, or sorry, sugar or salt into water and stirred it around a little bit? What happens? It dissolves. It's dissolution. Now, by the same token, what happens if I evaporate that water later? Yeah, the sugar or the salt recrystallize if enough of the water is gone, right? Once enough water is gone that those bonds can reform, they do. So the most common agent of chemical weathering is water with something else dissolved in it. Some common culprits here, oxygen. When you get oxygen dissolved into water, then that's what makes things rust. Okay, iron turns red. Copper turns green. You guys know why the Statue of Liberty is green? Yeah, it's oxidized copper. Good. How cool. Have you ever seen what show was it? There was a show that I watched where they made the Statue of Liberty out of iron instead of copper. And so she was red. Yeah, it was an interesting thought. Shows have so much fascinating There's some shows that they do really good, like the subtle parts of it. Like, there was this show that I watched maybe about a decade back. It was called Van Helsing. You guys you see that? The TV series on Sci-Fi? Oh, the movie with Hugh Jackman? Oh, that's always a classic. That's a fantastic movie. I'm talking about, maybe it was just called Helsing, but it was on the Sci-Fi Channel, I believe, which I don't even know if anyone watches that anymore. But they used to have some really good shows. Stargate, Helsing, all of those, okay? But the premise of the movie was that Yellowstone erupted and put an enormous cloud of ash into the sky. And in the first episode, you're watching it. There's this news: Yellowstone erupts. They evacuate half of the United States. You know, it's like this big catastrophe deal. The main character lives on the East Coast. It doesn't really affect her that much, other than she can look out of the window of the diner she's in, and she sees this huge like cloud of ash that's slowly advancing towards her, right? And eventually, it's going to cover half the planet, right? Like they're saying on the news. Well, the cloud of ash in the sky, this is kind of spoilers, but this happens in the first episode, so it's not that bad, right? The cloud of ash in the sky cuts off enough of the sun that all the vampires come out. And yeah, they all come out to play, and now all of a sudden it's vampires versus humanity, and guess what? Humanity loses big time. So it kind of turns into a Walking Dead sort of situation where almost everyone is becoming a vampire, and the few remnants of humanity have to survive somehow. But I loved that their premise for how this happened was the Yellowstone erupted. It seemed very inventive to me, and it kind of, as a geologist, it gave me that instant click with the show, you know? So anyways, I love it when they add little bits like that into TV shows. Okay, back to chemical weathering. So oxygen, very common. Carbon dioxide, also very common, increasingly common, right? As things progress in our world right now. More carbon dioxide dissolved in water makes carbonic acid. Believe it or not, carbonic acid dissolves things. Put enough carbonic acid in our oceans, and you get the unfortunate result of sea creatures that use calcite for their shells. The calcite starts to dissolve. Shells get thinner, brittle. They break apart easier. Those creatures cannot survive. They die. And you get mass extinctions. We see this in the fossil record. This is the path that we are on at the moment with carbon dioxide in the atmosphere increasing. It's going to make its way into the oceans. We are already seeing increasing acidifications of our oceans. This happens on land too. Water, rich in carbon dioxide, falls as a light carbonic acid. We call this acid rain. Have you heard that term before? How many of you think acid rain and think, oh, don't go outside, you'll get melted? Right? That's what the movies do, right? That is not actually what acid rain does. There is no form of acid that can fall out of the sky that will do that to you. However, carbonic acid in your rain is very common and will dissolve minerals, some faster than others. Calcite dissolves very quickly in carbonic acid, while things like feldspar do dissolve, but much slower. Okay. Most of the time, the two major types of acid rain that you'll ever encounter in your life are carbonic acid, which won't hurt you at all. You can drink it and you won't even notice. Matter of fact, you probably already do, right? And sulfuric acid, which really you only ever find in proximity to something like a volcanic eruption. It's pumping sulfur dioxide up in the atmosphere. It mixes with the rain, and then it falls like that. That will actually be more damaging to you. It won't like kill you unless you take a bath in it or anything like that, but I wouldn't recommend hanging out in sulfuric acid rain, right? Acid rain more commonly damages things like infrastructure, statues, gravestones, roads, buildings made out of limestone, stuff like that. Those are most often what acid rain will affect. As a matter of fact, caves are most commonly formed as a result of carbonic acid in the water, in the groundwater, that is making its way through a limestone bed. As the groundwater progresses through the system, and we will have a whole conversation about groundwater later in the semester, as it makes its way through the pores in the rock, any carbonic acid that was in that water will dissolve the calcite in that limestone around it, making a void. And that void we call a cave. How many of you have ever been in a cave? Was it Carlsbad? Yeah, okay. Carlsbad is a pretty good example for what a cave looks like. I'm a little bit of a purist. They've turned Carlsbad into a little bit more of a tourist trap than an actual caving experience. But if you want to see what caves look and feel like, I have plenty of videos of them on my YouTube channel. I am a guide with the Texas Cave Management Association. I do 3 or 4 trips a year out to various caves in our area, some as far south as almost to the Mexico border, and some out in New Mexico. We have a few not far away from here, actually. We have one out in Iran. That's usually where I take people to train them. It's a fairly easy cave, but it's where I take them to train them how to go into the more complicated caves later that year. I'm probably going to be doing a caving professional learning experience this semester. Usually I'll do it in March or April, depending on the weather. So if any of you are interested in seeing what a caving experience is like, let me know, and I can get you that information once I make it, once I put the details together. Okay, so let's look at some chemistry here. How does this happen? What does carbonic acid do and why? Well, I don't know if you guys can see that very well, so I'm going to color it. Okay, I'm going to make it a little bigger. CaCO3. This is calcite, a mineral that you all should be familiar with by now in Lab 1. Let's add to that our carbonic acid. We got some free hydrogens in the water plus HCO3 negative. Now, when we balance this equation, this is going to give us loose calcium ions and 2HCO3 negative. We call that a bicarbonate. You take a glass, you fill it with water from your sink. You don't have a water softener. How many people really have a water softener, right? Well, good for you, Marquez. The rest of us have to drink Odessa water. Just kidding. No, that's actually really good. Okay, so, but like I turn on this sink, I put a glass of water in it, and I leave it there for 5 days. What happens to the water? It's gone, right? We forget about that water glass, and the water's gone. You come back to it at some point, you're like, oh, I forgot about this water glass. The water's all gone, but what's left in it? It's like a white dust, right? But you're right. You know what most of that is? You know what that white dust is? It's bicarbonate. Yeah, it's bicarbonate. Matter of fact, you'd be hard-pressed to find any water from any well anywhere that didn't have at least a little bit of bicarbonate in it. We have a lot here. That's a big part of the reason why our city water has that famous taste, right? Okay, it's that bicarbonate. It's mostly harmless. There are a few things in there you probably shouldn't be drinking, but the bicarbonate itself, mostly harmless. If you drink too much of it, you will get kidney stones. Yeah, you drink too much soda and you drink too much Odessa water, you'll get kidney stones. How do we win here, right? Well, you could purify your water and you could just not drink soda. But I know, that's very hard. I actually don't drink soda. Judge me how you will. All right, so that's the chemistry for this. We'll come back and show you how that affects things like feldspar later. And by later, I mean the next slide. Okay, so you can see this a little bit clearer. And those of you that are watching this online, you can feel free to pull up the PowerPoints and follow along here. But here we have potassium feldspar. What do we find potassium feldspar in? Very common in things like granite. So let's say that this carbonic acid has encountered a granite as opposed to a limestone. Okay, so we have our potassium feldspar, potassium, aluminum, silicon, oxygen. Hey, look, it's our silicon tetrahedron, right? Our good old friend. Okay, with some potassiums and aluminums attached to it. Then we've got our carbonic acid plus the water that carbonic acid arrived in. What does that give us? We balance this equation. We end up with an aluminum, silicon, oxygen arrangement that we call a clay. Some loose potassiums, 2HCO3 negative. What do we call that? It's that delicious thing in our water. Bicarbonate, okay? And then some loose silicons. We're taking a light silicate mineral and then introducing it to something that reduces it, dissolves it to its constituent elements plus a secondary mineral that we call clay. This is chemical weathering. Okay. Now what happens to all these things? This clay goes on to form the basis of much of our soil, which we will talk about here in a few slides. The potassium, plants love absorbing potassium. That usually gets gobbled up by some plant that's utilizing that water for some reason or another. Bicarbonate, usually will just stick around in our water, right? And then that silica, what happens to that loose silica ion? Well, some of it makes it out to the ocean to be utilized by creatures out there, but a lot of it ends up staying around in our rock, making rings around different voids in our rock. And that silica builds ring after ring after ring after ring after ring until that entire void, that hole in the rock, is filled up with silica. And that's what gives us agates. That's where these come from. You ever seen these before? All sorts of colors, and you see those lovely patterns in there? Yeah, you find these all over the world because this process happens all over the world. That's where this comes from. Okay. Hawaii has red dirt. Do you guys know that? How many of you have ever been to Hawaii? You've never been? Okay. I lived there for 3 years. Take my word for it. Hawaii has red dirt. Why does Hawaii have red dirt? Use what we just learned to solve this mystery. You are the Hardy Boys. You are Nancy Drew. You're the Scooby Gang. Solve the mystery. Why does Hawaii have red dirt? Iron is red because it oxidizes red. Why would there be oxidized iron in the dirt? What do we know about Hawaii? Ooh, you're on the right track, but you're saying the wrong words. What about Mayfic? What is Mayfic? It's okay, Marquez. Don't beat yourself up. That's okay. It's okay. You can say things wrong. Don't think Fe, think FEL, feldspar, right? What about Mayfic? What is Mayfic in Hawaii? What? Say it louder. Volcanoes. Hawaii is a volcanic island with what kind of magma? What composition? You just said it. You said mafic. It's got mafic composition magma. Mafic is rich in iron and magnesium. Therefore, that magma and lava in Hawaii is going to make mafic rocks. And those mafic rocks are going to chemically weather into red dirt. Red because of the iron, and dirt because of the clay. Look at this. Quartz is going to eventually become just loose silica ions that are going to make those agates, right? Feldspars, light silicates, are going to make clay minerals with a few extras that go into the water. Amphibole, here's our first dark silicate here, is going to weather down into clays plus iron oxides, limonite and hematite. Olivine, also a mafic mineral, is going to weather down into limonite and hematite. Our dark silicate minerals are going to weather down into iron oxides and clays, aka vis-a-vis Hawaii has red dirt. Mystery solved. You can figure out things about your world, basic things like, why is this a thing? Well, I learned this, this, and this. Let's tie them together, and that gives us an answer. It's like a logic train. That's what I call them. These are logic trains. You're making different stops along your route to end up at your eventual destination, but you couldn't get to your destination without the stops along your route, right? You're learning all these things you can tie together to answer the questions about your world yourselves. Cool? Cool. So cool. Okay. Spheroidal weathering is one way that you can see chemical weathering. When some chemical agent in your water percolates its way into the rock, sometimes it will have an effect where it causes your rock to swell in some places. Like, have you ever seen mold get into wallpaper or into drywall and it starts to bubble up? Y'all need to visit some houses from the early 1900s, I guess. Okay? Huh? J.K. Rowling? What about her?
One time she posted like a picture of herself in her house, and there was black mold on the walls, and everyone made fun of her for it.
Black mold is not healthy for you.
Not very good.
No.
Everyone made fun of her. They said her brain was infected with black mold.
Oh my gosh. I was helping someone tear down. I was at a service project. So I was helping someone tear down their house, and we pulled down one of the walls, and it was just filled with black mold, like the kind that's like stringy and like everywhere. It's not just like a mat. It had actually made like one of those stringy colonies, and there was like stuff in the air. And we evacuated that place. Like the police and the local health organizations like cordoned it off. We had to get tested to make sure none got in our lungs. It was a whole thing. Black mold is not good. All right, so, but it will start to bubble up, and as it bubbles up, it'll kind of start to crack and fall apart in these layers. We call this spheroidal weathering. Okay, any questions about chemical weathering? Great, let's move on. Let's talk about weathering rates, be it mechanical or chemical. Which of these gravestones is older? Pretty obvious, right? You're right. Okay, yes, that one, right? That's the oldest one. It's actually not. This is the older one. Why does that younger one look like it's so much older? Why does it look like it's in so much more of a worse shape? Because of what? Environmental conditions are a big factor, but the biggest factor, what it is made out of. It may not have been cheaper, right? And this is how they get you, okay? I already taught you how to not get scammed by a countertop salesman. Now I'm going to tell you how to not get scammed by a gravestone salesman, okay? You learned so many useful things in my class. Okay, so this gravestone is made out of granite. Feldspar, amphibole, quartz, right? This gravestone is made out of marble. Calcite. Ew. Marble is beautiful, which is probably why they sprung for that, right? But unless you know, unless you've studied it, unless you've bothered to find out, you don't know that marble is made out of calcite. What's the hardness of calcite? It is definitely below 5.5. It's a 3. Fairly soft. You could cut it with a butter knife if you had enough pressure behind it. Like you just chop at it with a butter knife. It'll fall apart. Okay? Also, we just learned something about calcite. It dissolves very easily in what? Water containing carbonic acid. And there's a lot of carbon dioxide in the atmosphere. So there's a lot of carbonic acid, even if it's just a light one. So after decades and decades and decades of this gravestone being subjected to rainfall after rainfall after rainfall of carbonic acid-rich rain, it looks like that. Whereas this older one, made out of granite, looks hardly affected whatsoever. It is very slowly getting weathered, but not nearly at the same rate. This is weathering rate. You already know all of these minerals have different properties. You already know all of these minerals have different melting points and crystallization points. Each of them also has different weathering rates. The factors that control weathering rate, what the mineral is, what its environment is like, how much rain is there. If it's an environment without much rain, it can't get subjected to that much carbonic acid, right? So a gravestone made out of marble in Odessa would survive a lot longer than a gravestone made out of marble in the Amazon rainforest, right? Why? Because we simply have less rain to expose it to. Okay, so environmental conditions are a big factor as well. Okay, this is differential weathering, is what it's called. Just like we learned about differential melting, Differential weathering is a thing as well. Okay, what questions do you have about weathering or erosion before we move on to talk about soils? No? Nothing? Your cup kind of matches your sweater. Except I think that's cheetah pattern and that's cow pattern, right? Okay, it looked like it matched. Okay. What is soil then? Riddle me this. Very small rocks? Gee, how small are we talking? Microscopic? Soil is made out of microscopic rocks? Weathered rocks. I like that terminology better. Can we use that terminology? I know what you were going for, but as we're learning this terminology, we should use it, right? So we're clear. Yes. Aha! So it's not just weathered rock material. There's also organic material. There's a whole lot of stuff in soil. Soil itself is the material that is on the exposed surface of our planet, the continental surface of our planet, okay? You don't have soils in the oceans, at least not anything that is usable. We rely on soil. What do we use soil for? Agriculture. We can't grow stuff without it. Any crop relies on soil. Crops feed us, crops feed our animals, which we then go on to eat, right? Every aspect of our survivability as a species relies upon soil, which means that maintaining soil and understanding that soil well enough to take care of it, right, is very important. Soil studies, very important, okay? So, soil itself is a combination of 4 things. Rocky matter, mineral matter, okay? So the weathered, broken down rocks that make those minerals that go in the soil, like those clays. Humus, not hummus. It's not a delicious Greek chickpea dish, okay? It is humus, is the organic content, like Abby was saying, okay? Partially decayed organic material. And then there is air and water. Those are the 4 things you need to make a soil. Now, the different proportions of those will make different soils depending on, what do you think? What will determine the proportion of those things in the soils? Huh? The environment. Bingo. Exactly. Do you think that a soil in Odessa has more air or more water in it than a soil in the Amazon? More air. You think that the soil in the Amazon has more water. Also, the soil in the Amazon has more organic content. Don't worry, we'll come back to that later. Okay? So it is this balance that has to be maintained, because if it is thrown off, then the things that are living there may not be able to survive there anymore, and new things move in because it is soil better suited for them. Right here, where we are standing, there used to be thriving forests. Yeah. Before that, long before that, there was an ocean. Before that, thriving forests again. Things change because Earth is dynamic. Tectonics happen. I should make bumper stickers, right? Tectonics happens, right? Y'all would laugh if you saw that on the street, wouldn't you? Physics happens should also be a thing, yes. I'll just, yeah, Professor Hart's funny, not so funny shirts, yes. You would have to have been there jokes, yes. That'll sell really well. But these things all happen, and as in the long run, you go from ocean to desert to forest, sure, but in the short term, you can go from, say, a 5% quantity of water to a 1%, and all of a sudden you're in a desert. And then at some point, maybe in a couple million years, you get more rainfall and you get a 7 or 8%. And so now you're in a sort of swampy, grasslandy sort of soil, right? Those things happen, those minor fluctuations happen over the short term all the time. And so we could go from, say, a grassland in West Texas to a semi-arid desert environment, right? Okay. Now, the formation of soils includes your mineral content. Your mineral content is determined by the parent material. Weathered material comes from something initially, right? It doesn't just pop out of nowhere, right? I was about to say it doesn't pop out of the ground, but it kind of does, right? But it still has to come from somewhere, okay? Something has to break down to make that material. If I have a granite, that granite, the chemical composition of that granite is going to determine what the chemical composition of the mineral component in my soil is. Basalt will do the same thing, hence why Hawaii has very iron-rich red dirt. The longer the time has passed, the more time this is a better way of saying it, the more time that has passed between the initial weathering of that rock and the formation of that soil, my soil is going to resemble chemically, it's going to resemble that parent material less and less. So a really old soil, it's hard to tell what it's from. But a really recently made soil, you can tell pretty carefully, pretty easily if you do a chemical analysis. So if I have a rock that breaks down way upstream and that mineral content, that clay, that sand, whatever it is, gets carried downstream by this river and gets deposited somewhere over here and eventually becomes part of the soil way down here, we are going to call that a transported soil. Not because the soil was transported, but because the mineral component of it came from somewhere far away before the soil was made. How do I know that? Well, if it's a chemically related granite originating material, so the soil is made from mineral matter that came from a granite, but the nearest granite is a pluton exposed 100 miles upstream, that's the only source it could come from, it's a transported soil. Or you can have residual soils, which are the result of local rocks that break down, and their sediment is incorporated into that soil. Residual soil is made from local rock. Transported soil, the mineral component, comes from somewhere far away. Now, like I mentioned earlier, the environment is a huge factor in determining the characteristics of your soil. For example, your climate will determine how much water content, how much air content, all these things, okay? But also, that biological component, that organic matter. Do you suppose we have a lot of organic material or very little organic material in our soil here? Yeah, it's on the lower end for sure, unless we add things to it. What do we call adding things to it? What do we call it stuff we add to it? Fertilizer. This is what fertilizer does. Fertilizer artificially changes the balance of your soil to encourage the growth of plants that would not naturally grow here, right? Alfalfa, soybeans, corn, our soil is not ideal for a lot of these crops, but we grow them here because we artificially adjust our soils to compensate. Nature does this too, by the way. There are certain bacteria in soils that can change the balance of certain chemicals in the soil and make it easy or hard for certain plants to grow. There are certain plants that do this as well. Pine trees. Y'all ever seen a pine tree? A fir? You know what I'm talking about? Have you ever had a Christmas tree in your living room? Okay, that's a fir. Okay, the plants that live way up north. Okay, the forests of pine trees look like that. We don't really have those here. There's a bunch in New Mexico though. If you ever go over there, okay, go to the Guadalupe Mountains. You'll see a bunch of these. Okay. But, or out in Cloudcroft. You ever been out to Cloudcroft, Ruidoso out there? Tons of those. Okay, they like living in higher altitudes. So what do though? They have this fascinating evolutionary trait that they developed some time ago. Hard to tell exactly when. But their needles, those pine needles that they have instead of leaves, when they fall to the ground and they start to break down, biologically break down, they put an organic acid into the soil. This acid leaches into that soil and makes it really hard for any other non-pine tree plant to grow. It is hostile to those roots. Any seedlings that try to grow in that soil, the acid pretty much kills off their roots very quickly. And so if you ever go walking through a pine forest, you'll notice there's very few other plants that live in that forest besides pine trees. You will see some though, but these are plants that have, in this evolutionary arms race, themselves evolved to survive in such acidic soil. If you wanted to grow, say, an apple tree or a pear tree in a place that has had pine forests for millions of years, good luck. You have to change the soil. This is something that my parents went through when they moved to North Idaho. My mom wanted to have an apple and pear orchard. But guess what? North Idaho has had pine trees for millions and millions of years. So the soil is well and truly infused with this organic acid. So her first few attempts, all the trees died pretty quick. So she had to dig up all that soil and then put a whole bunch of crushed limestone in it. Why would crushed limestone change the acidity of the soil? The acid dissolves the limestone, right? Like we just saw. And by dissolving the limestone, the acid is, I guess you could say, it's all used up. It's neutralized. Crushed limestone is a great acid neutralizer in many things. We use it to neutralize the acids in soils and make them better for other plants to grow in. Also, how many of you bake with sugar? Right. Miriam, you said you like to cook, right? Use granulated sugar, right? Did you know that part of the sugar making process involves crushing up the beets or the sugar cane, making a sort of sludge out of it, like a liquid, and then allowing it to ferment for a little bit? But as it does so, it has a whole bunch of acids in it. Those organic acids from the plants. How do you neutralize those? You have to mix in crushed limestone. It neutralizes the acids, and then you mix it with a whole bunch of water, and then you can, remove all the stuff like the neutralized limestone components and stuff like that. There's another process, but you have to get rid of those acids first, and that's what limestone is used for. We use crushed up limestone to neutralize the acids in our sugar before it goes to you in the store. Yeah?
What about like decomposition? Is that like affects how effective the triangles are?
Decomposition is what releases the organic acids into the soil. So it's part of the process. Yeah. Interesting, huh? Topography is another component of this. Topography is basically the elevation change that occurs over distance in an area. So if I were to say that's a steep hill, I am making a comment about the topography of that hill. Okay. Steeper hills, do you think that steeper slopes will be able to have more or less soil on it? Less. Why? Right. Water and wind and gravity, it's going to carry it all downhill. What about if I have a very flat slope? Good soil, lots of soil, healthy soil. What do you think? Ah, there it is. We'll get a swamp. We'll get a bog. Why? Because the water can't run away, and so it sits. You'll get a sort of boggy area. Ideally, the topography would be a gentle slope, not enough to carry away our solids, but enough to allow the water to percolate away over time. Okay. Also, is my slope oriented towards the sun or not? On a flat surface, you'll get the sunlight all day long. But if I'm on a slope, I only get however much sunlight during the time of day that the sun is facing that side of the hill. All of these are factors determining the health of the organic material that goes into my soil. Also, the more plants that there are that live in that soil, the more that they hold it together and bind it together, and the less likely it is to get carried away. Now, when you go digging through soil, the first thing you're going to notice is, well, one of the first things I would say is that as you're chopping through your layers of soil, you're going to notice that there are different colors of soil. Close to the top, you have very dark, rich brown layers, which we call topsoil. This includes the O horizon, which is our decaying organic matter, and then the A horizon, which is the stuff that our plants like, right? They grow in that, okay? This is our topsoil. Underneath of that, we have the E horizon, also known as a zone of alluviation or leaching. It's going to be very pale, kind of whitish color. And then underneath of that is the B horizon, This is where all the unused stuff goes. The clays that no plant really uses. It uses a whole bunch of other stuff, and over time, the unused clay particles just kind of get shoved down there, and that's where they stay. Different environments are going to have different thicknesses to each one of those. For example, in the Amazon rainforest, are there a lot of plants in the Amazon rainforest? Yeah, there's a few. There's a few. I've heard that there are a few. In fact, a few. This is going to make a very thick O horizon where all that organic material is decomposing. Very thick O horizon, as opposed to here, where we have practically none, right? That O horizon goes on to make a lot of organic rich material in their A horizon, which is not nearly as thick, but is very rich in their organic material. And then underneath of that, they have a very thick E and B horizon. Why? Because the plants don't really live long enough to send their roots way down deep. The plants in places like the Amazon rainforest instead live for very short periods of time with shallow root structures that live mostly in the O and the A horizon, meaning that mineral content is very poor, but organic content is very rich. They just keep recycling the same nutrients through the O and A horizon. Whereas here, we have very little O, very little A, a lot of E and B. Okay, and so we have a different type of plants that can survive in that environment. There are, come on. The whole thing's frozen. Okay, there are 19,000 different types of soils that have been identified in the United States. Every country or group of countries has their own different classification method. There is no universally accepted one. Maybe that'll happen at some point, but there are about 19,000 in the United States system, which have been, broadly categorized into 12 orders. I do not require you to know any of those, so don't worry about it. I provide the 12 orders for you on what is supposed to be showing up as the next slide. Does my mouse even work? Can I close the PowerPoint? Catch up. There we go. Okay, so here's your 12 orders. Now, because soil is so important to humanity, we put a lot of time into studying it and understanding it, right? We have learned through hard experience what it means to not take care of our soils. Here you have some clearing of rainforest. This is actually in the Amazon. Notice how they did not have to go very deep to reach that pale colored E and B horizon, right? That's not the dark, rich O horizon or A horizon. It's not very thick in the rainforest. But after you remove that O and A and all the plants, there's nothing holding that soil there. And so the next time it rains, that's going to get washed away. You ever seen a picture of the Amazon River Delta where it goes out to the sea? Amazon River Delta. Check this out. See that? What do you see? What color is it? Did you notice what color that soil was that we saw after the clearing? It's the same color. All that soil is getting washed out to the ocean, which means it can't be used by plants. It can't be used by us to grow anything. And it's really choking up the rivers, affecting the ecosystems there. And do you think that's really supposed to be out there in the ocean? Let's see if we can find a picture of.
So that's why the trees don't ever regrow in the rainforest when they're cut down.
It's difficult to replant trees in rainforest that has been cleared away. Yeah. Yeah, look at this. This is a good picture right there. This is from space. Look at all the soil that's getting washed out into the ocean from the Amazon. Think that's good? Probably not. It's not an ideal situation, to be sure. Now, for a long time, people that live in rainforest areas have actually used that mud that they can make from that as bricks. Why? Because when you compact it together, those clays, the form of a clay mineral is very flat. So when you compact it together and orient those clays with a lot of pressure, you can make a very water-resistant barrier. So they do that, they make bricks out of it, they fire them, and then they can make structures that last for a long time. This city's like 800 years old. This is Angkor Wat, I believe. Okay, it's like 800 years old. It's very old, lasted for a long time because it's made out of very sturdy material. The same thing happens naturally. Those clays can orient themselves to be flat. Given enough time, this happens in those E and B horizons. When there's pressure on it, they reorient themselves to be flat. Because they are flat, water cannot go through them. It cannot soak in very easily. This happened here. We have a lot of clays exposed on the surface. That's why whenever we get a bad rainfall, it floods very easily. Not only is the Odessa drainage system not that great, but also the soil under our surface is made out of a lot of clays. And so the water cannot leach in very easily, and so it builds up on the surface, and we get flash floods in the city. Okay, it's very common in desert areas. Soil erosion. So the removal of soil is a growing problem. Did you get that joke? You can't grow if there's no soil. Right? Yeah. No? Okay. Yeah, I'll put that on a t-shirt. Yes. Everyone just look at it and go, oh, yes, very true. It's like, fine, sure. It's a serious shirt now. Okay. The Dust Bowl, the 1930s. You probably heard about this in school, right? What was the Dust Bowl?
The farmers were growing plants that would deplete the soil nutrients.
There was a lot of overuse of the soil in the American West and Midwest and parts of it, right? In combination with a terrible drought that happened for several years in a row. The soil was dry, it was overused. A lot of the stuff that was holding it together was being overused and by all the crops. And so what happened was the wind that we get a lot of out here, right, picked up all of that dust and blew it all over the place. Towns got buried, cars got buried on the highway for years. Terrible, terrible dust storms out here in this part of the country. Okay. It removed so much soil over, I'm talking millions of acres, okay? Where this guy's arm is right now was the surface of the ground before the Dust Bowl. Where he's standing now is where it is at now. Imagine that much soil being removed from millions of acres and just blown hither and thither. So that was kind of an eye-opener. People have known for a long time you got to be nice to your soil. That was a big eye-opener because you lost a lot of arable, aka farmable land as a result of this. No one could farm where there wasn't soil. We have had to work a long time to recultivate the soil since this happened. So what can we do to prevent stuff like this, to prevent the loss of our soils? There are a few things we can do. 24 billion tons a year of soil are lost to the ocean. 24 billion. Back in 1990, I believe it was 9 billion. The rate at which we lose soil is increasing, largely because of poor stewardship techniques, but also because of deforestation. The plants binding that soil together are not there and allowing the water and wind to carry it away. And eventually it makes it out to the ocean. what that soil comes with is also a problem. That soil can fill up bodies of water. If I have a dam, okay, so here's a side view. Okay, so here's my reservoir, here's my dam, here's the top of the reservoir. If I have more sediment coming into this area, that sediment starts to fill up the bottom of my reservoir. Where's the water going to go? If I have a glass of water, and that glass of water stops half an inch from the top of my glass, and I pour 1 inch of sand in that glass, what's going to happen to my water? It will overflow my glass. The water is going to go up, but it can only go so far up before it also goes out. It leaves the bounds of the reservoir to make room for it because the sediment is taking up so much space. And what happens to the farms and the communities and the churches and the towns and all the people that live on the sides or near that reservoir or lake? They get flooded out. Now, what also happens if the soil going into there is full of pesticides or over-fertilized? You bring a lot of nitrates into a body of water. You know what loves to eat nitrates? Algae. You get algae blooms. The algae blooms consume all the oxygen. You get an anoxic water environment. You know what can't live without oxygen? Just about everything, right? And so your fish die, your crustaceans die, your entire ecosystem in that body of water dies. This is all cascading. This is all an effect of the result of poor soil stewardship. So what can we do to prevent that? Well, there are a couple of practices that are commonly implemented. Windbreaks, for one. Have you ever gone along a farm or a ranch and you've seen that they have this long line of trees or very tall, thick bushes next to their fields? Oftentimes, this is another crop that they can use. Like they'll have pecan trees on the, around their other orchards or their crops, like corn or whatnot. Okay? That's a windbreak. The trees are absorbing the energy of the wind so it doesn't get into the fields and carry the soil away. That's a windbreak. Then you've got steps. You can make this sort of terracing effect. If you have a large property on your hill, you can basically cut steps into it, and you can have your crops on the steps so that every time it rains and it starts to carry the soil away, instead of just carrying it all away at once, it carries it down to the next step. And then the next step after that. And then the next step after that. And this sort of terracing effect preserves and prolongs how long you can use that soil before it is just gone. And then there's crop rotation, which I believe you mentioned. Crop rotation. This is actually something that we owe a lot of the research for crop rotation to our founding fathers. Crop rotation, in simple terms, let's say my property is divided into quarters. Half the year in 1, 2, 3, and 4. Oh, that does not look like a 2. 2. Okay, in 1, 2, 3, and 4, half the year I will grow beans in 1 and 4 and corn in 2 and 3. Beans put a lot of nitrogen in the ground. Corn takes a lot of it out. So if I'm having trouble balancing the nitrogen in my soil, then the other half of the year, I'll do beans in 2 and 3 and corn in 1 and 4. That way I can continually use my soil to make profitable and necessary crops without overusing my soil to the point that it becomes useless and we get another dust bowl. This is crop rotation. You find crops that complement each other. One puts something in while the other one takes it out. And you got crop rotation, baby. Corn and beans, that's just one example. Do you know the number one reason why rainforests get carved up? Why rainforests are cut down? Farming, okay. Greedy corporations doing what? Needing what? Wanting what? Getting what? Huh? Lumber? I wish that were true. A depressing amount of all the trees that get cut down in the rainforest get burned, actually. There's a lot of valuable wood, beautiful wood. It gets burned because it's not the most valuable thing there that they're looking for. Some of it gets sent away to get turned into things, but a lot of it gets burned. Living communities, no, that may be a result, but not really. Not ranching, not farming. Some of that may happen as a result of this, but the number one reason why rainforests get cut down. Something in the ground, indeed. This is called bauxite. Do you remember what the first element in our clay chemical equation was? What is Al? Yeah, that is. So what element is Al? Aluminum. We have so much aluminum on our planet. It's very common on the crust, but it's dispersed all over the place. We find it in ones, in so many other elements. It's not really enough to pull it out, but you know what is rich in aluminum? Clay. Do you know what has a lot of clay? Rainforest soil. Do you know what doesn't use a lot of that clay? The rainforest plants. And so rainforest soil is thick deposits of aluminum-rich clay. And as time goes on and the groundwater makes its way through that clay, it dissolves out a lot of that aluminum. And then somewhere under that rainforest, it gets deposited and you get thick layers of aluminum-rich ore called bauxite. Aluminum, very strong, very light. The lightest metal we have. Think about all the things in your life that use aluminum. Your laptop cases, your glasses, space shuttles, bicycles, airplanes. Aluminum is one of the most valuable metals on our planet because it is so versatile and so light, right? So the number one reason why rainforests get chopped down? Aluminum. Now, it's great when we can find a bauxite mine where a rainforest used to be, but you know what you have to do to find where a rainforest used to be? A lot of detective work, including digging, core samples, all of that. We do find those, and it's great to build a mine there, but you know where we know for sure bauxite is right now? Under rainforests that exist right now. So that's why. I'll pass that around, actually. Take a look at it. There has to be a happy medium. If we do not get aluminum, it is very hard to progress our technology the way that we understand and have it now. Just the same thing with the oil industry. It's the same thing with gold mining. It's the same thing with every other mining. It's destructive, but we need it unless we want to consign ourselves to living in the Stone Age again. I don't want to do that. Plastic, be very hard to give up, but gosh, we got to do something about all these emissions, right? We have no aluminum, we make no spaceships, we make no airplanes, but, you know, we stripping the rainforests? I hope that you're getting that there's no easy answer here, but there has to be a balance. And it's up to future policymakers and scientists and concerned citizens to work together to find that balance. And I highly encourage all of you to be at least one of those things. Okay? All right. That's all I got for you today. Any questions? All right. Well, I will end the recording here and go into my office for my training. If my online students have any questions, you know, you can always ask them here in GoReact or send me an email.